our kind of crowd.
All right.
Shall we see?
Sounds good.
All right, so let's start with this. There's a lot of stuff named quantum. There's quantum computing, quantum encryption, quantum networking. Why don't you give us like a high level, what is quantum computing and how is it different from this other stuff named quantum?
Sure. Yeah, so there's, like Gustav said, there's a lot of quantum technologies emerging. Quantum computing in particular harnesses quantum dynamics and quantum effects to do a computing task, to do a calculation, to provide a capability to solve a problem, put that capability in the hands of a user. So our mission at D-Wave is to make quantum computing easy to use for our customer base. But at the core, it's a computing technology. You have a problem that you want to solve, you're running a quantum algorithm, you're getting an answer out. So this is different from, say, quantum networking or quantum encryption or quantum communications. There are technologies and there are firms that are commercializing technologies for quantum communication where you're able to send via quantum encryption information in a secure way between two parties. So fundamentally, you're harnessing quantum properties and quantum effects to produce this secure communication, but the end goal is very different. In one case, it's computing, it's actually solving a problem. In the other case, it's securely communicating a piece of information between point A and point B, between two parties. And quantum networking really is kind of the infrastructure that enable the quantum communication piece, so that enable two parties to communicate in a quantum encrypted way.
Cool. So Trevor, we got this picture behind us. You want to tell us what that is?
Yeah, so this is a picture of D-Wave's advantage to annealing quantum computing system. So this is our sixth generation annealing quantum computing product. We chose to initially focus on annealing quantum computing because we saw this as a faster route to commercial quantum computing at scale. So at the heart of our system is an integrated circuit that's about the size of my thumbnail, so very similar in size to, say, the chips that are in your laptop or your phone. The difference between those chips and the chips that are at the heart of our system is that we're using superconducting circuits. So superconductivity is a process by which, or is a property by which some materials exhibit a zero electrical resistance if you cool them to a low enough temperature. And so this allows you to build the building block of quantum computing systems, qubits, out of superconducting circuits very easily. And with superconducting quantum integrated circuits, you can basically harness all of the technology development that's gone into producing the digital world around us today. So all of the photolithographic techniques, all the manufacturing techniques, all the packaging techniques, we've just tweaked them and adapted them so that instead of a semiconductor processor, this is a superconducting processor. So in this image, behind the kind of the D-Wave logo, that's a gold-plated shield that serves as a shield around the integrated circuit, is about the centimeter by centimeter square superconducting integrated circuit, and then all of the wiring or the I/O infrastructure around the sample holder here are just means by which we deliver signals down to the integrated circuit. So one property of superconducting systems is they need to be cooled. They need to be operated at cryogenic temperatures. And so this entire assembly is mounted inside a refrigerator to keep the system cold. And so all those wires need to be carefully heat sunk as they're coming from our room temperature control electronics down into the system. And so we've done a lot of engineering to make sure that we can keep these chips cold. We can keep them well isolated from interference that will affect the quality of the calculation. But this is now routine. This is basically production ready. So we've had systems that are up and available in our cloud service for years at a time. So, and this is a lot of engineering has gone into this process. Now, superconducting qubits are only one modality and one way to build a quantum computing system. At D-Wave, we see a massive long-term advantage in using superconducting approaches. But if you're following the rapidly maturing quantum industry, there are some other approaches to building your qubits. So we chose superconducting qubits. For example, companies like Quantinuum, RNQ, they're building their qubits out of trapped ions. So they're cooling ions, atoms that have an electrical charge, and each one of those individual atoms is acting like the qubit, the quantum bit. There's some companies that are doing the same thing but with neutral atoms, and there's companies like PsiQuantum and Xanadu in Toronto that are using photons, so basically light, to encode that quantum information. But at the core, the idea is that you want to build your quantum bits, your qubits, out of something that you can scale out to a large-scale technology, something that you can program, is something that will allow you to run quantum algorithms to solve a hard problem.
And so let's talk about qubits for a minute, because not all qubits are created equal, right? So we at D-Wave are pursuing both paths. Annealing is our current and available technology, but there are also the so-called gate models. You want to talk a little bit about what's the difference between those two?
Yeah, so I talked about kind of the different hardware modalities for building qubits. Okay, so I was right, there's different architectures or approaches to harnessing your qubits to do a calculation. So we chose annealing quantum computing systems and as our initial development program because in some ways it's an easier technology to scale. So annealing systems are naturally resilient to errors or fluctuations, and so you don't need to build in error correction to get to quantum utility. Annealing systems, the detailed controls, the I/O required to control the qubits and to manipulate them to run an algorithm are quite a bit easier to engineer for annealing systems than for gate model systems. And probably the most important aspect of annealing systems and what really kind of drove our investment is that we saw a fast route to commercial viability because there's a natural set of problems broadly in the class of hard optimization problems that map very nicely onto annealing architectures. So in terms of optimization, the idea is that you've got some objective function. So say you're an airline, you're trying to route planes between cities, you're trying to map planes from your fleet onto the routes. That's a hard problem as the number of planes and cities grows. So that at the core, the goal is you want to produce a mapping that does optimizes something. So your fuel cost, the amount of downtime, the total travel time between cities you want to minimize. And so you really want to optimize over like a fairly significant configuration space that actually blows up combinatorial or blows up very quickly as you add variables. So this optimizing these hard combinatorial problems are kind of a natural fit for annealing technologies. A lot of the rest of the industry, and we at D-Wave a couple of years ago also launched our own gate model quantum computing initiative. So this is the model that, say, Google or IBM or IonQ are pursuing. So gate model systems we see as complementary to annealing systems, and that the really exciting use case from my perspective is quantum chemistry. So the ability to actually calculate the behavior of materials and molecules inside your quantum system ahead of, say, producing them in the lab. We think this is really going to shortcut, say, drug discovery, materials discovery. A lot of the kind of the material world around us can be simulated by a large enough gate model system. But there's a catch. So gate model systems are much less resilient to errors. So fluctuations and interaction with the environment, not operating at zero temperature, any glitch can tend to invalidate your entire calculation. And so gate model systems need something called error correction. So you need to encode logical qubits by ganging up together a lot of physical qubits. And so there is a massive resource overhead and a lot of overhead classically, both physically and on the decoding side, to enable that error correction to get that resilience. And so this is a fundamental sort of a technical challenge that needs to get solved before gate model systems can really deliver utility. But at D-Wave, we're also very excited about the gate model modality. And so we launched our own development program. And again, we see these technologies as not in competition. They're complementary. Annealing systems are delivering value today for optimization. Gate model systems we really see as the quantum chemistry and quantum simulation being the killer app in several years.
Is it fair to say in my non-PhD lingo, I explain this as, you have a flathead and a Phillips screwdriver. They both do different jobs, but they're both useful in different circumstances,
Yep,
right?
Exactly.
So, and when I started learning more about the difference and what we're doing in, logical qubits and physical qubits and available qubits, what is so special about the fact that we use quantum bits, qubits? Is it superposition? Is it both 1 and 0? How do we explain this?
Yeah, I mean, this gets at the core of why people are excited about quantum computing and quantum algorithms in the first place. Like, why would you even care about quantum systems? I think the field really got launched in the late early 90s with the publication of an algorithm called Shor's algorithm. And Shor's algorithm basically postulated a particular set of hardware, a set of quantum computing hardware, a network of qubits, that if it had certain properties, you could run an algorithm that would allow you to more efficiently factor numbers than the best known classical approaches. The best known classical approaches, there is an exponential cost in the worst case to factoring large numbers, and this is the basis by which all of our modern encryption works. So it's a hard problem to take a large number and figure out what the prime factors are. And so Shor actually showed that you could do this efficiently, and this worst case became dramatically easier with quantum hardware. So this really got a lot of attention. This really was the impetus for the start of the global effort to build quantum computing technology. And at the core, quantum bits basically are very different than the bits that are encode information in the chips that are in your phone or in your laptop. And then exactly like Gaston said, you can actually put a qubit into the 0 state, you can put it into the 1 state, but you can put it into a weighted superposition of both of the states at the same time. And so in the case of annealing systems, if you've got a network of qubits where you have interactions between the qubits, this really fundamentally and vastly speeds up the search space or the search effort over trying to find an optimal answer. You're able to actually search much more efficiently because you're using qubits as your decision variables instead of bits. In the case of quantum chemistry, this allows you to actually represent the behavior, the physics speakers, the Hamiltonian of these molecules. You can actually directly encode in these superposition states. And so this really allows fundamentally an acceleration. So you're harnessing a new set of physics, quantum physics, to accelerate computation. So the algorithms that you're running are still, you're inputting data, you're getting results back, but the core computational engine is fueled by quantum physics. And so that's really the excitement. And there's now proofs and there's growing empirical evidence that there's tasks that quantum computers can do today that are just not feasible by any classical approach. So as this field emerges, you're going to see that gap continue to open, and there's a fundamental set of capabilities that are just beyond the scope of classical systems.
So that's what folks refer to as quantum supremacy, right? It's basically showing a process that in a classical machine would either be impossible or take a considerable, enormous amount of time, right?
Exactly. But I think for a lot of the customers that we've talked to, the quantum supremacy is exciting. It gets kind of their foot in the door, but what they care about is that they have a hard problem. They want to solve it. They've got a time budget. They've got a budget. They need to have this problem solved, and they need it solved. If you can show that you can solve this problem for less money, higher quality, and faster than other approaches, that's fundamentally what they care about. So the bar doesn't need to be in the supremacy regime. The bar just needs to be, can you deliver some advantage with this capability over existing approaches? And so this is really what's so exciting, and kind of what has kept me at D-Wave for 18 years, is that we're actually starting to see that commercial viability of quantum computing, so that we're putting this technology into the hands of our customers, and they're seeing value in using the technology and solving these problems.
Yeah, so I was recently in our lab and taking some folks through a tour, and one of the machines that was there, was pointed out to me, has been active in running production use cases for 5 years, uninterrupted.
Yes.
Right? So we've got some people in production use cases, and they're running optimization of hard problems. Like, can you talk a little bit about what kind of advantage they got out of that?
Yeah, so one example is one of our customers, Ford Otosan, they run a production line for mid-sized vehicles. So Ford Otosan is a joint venture between Ford Motor Company and Koç Holdings in Turkey. So this is a factory line that's in Turkey. And they have a hard optimization problem in that this production line is heterogeneous. So they're switching in between vehicle types. So they can produce different classes of vehicles, but there's some overall cost to switching the factory line between vehicles. And so what they wanted to do was be able to schedule vehicle production runs with many hundreds, up to 1,000 or many thousands of vehicles at a time, but optimize the switch between vehicle types subject to some hard business constraints. So there's supply chain fluctuations, so parts are coming in, parts may not be available, and so you want to make sure that your factory line is producing vehicles for which you have parts in-house. You want to basically schedule things subject to kind of maintenance and downtime on machines and equipment in the assembly line. and you've got a demand curve that's fluctuating. So you might get a bunch of orders for a particular vehicle type. So you want to make sure that you can minimize the number of times you're switching this factory line between vehicle types, but still subject to all of the business constraints and hitting your demand. So this is a hard optimization problem that was taking them well over half an hour, sometimes up to the better part of an hour to solve, just scheduling these thousand vehicle production runs. Moreover, their approach that they took with traditional computing was they really had to reduce or remove some of those hard business constraints. So they weren't representing the full complexity of the problem. So they actually worked with us and our professional services team to formulate a solution that uses our quantum hybrid solvers. And they got that solution time down to under 5 minutes, but they're able to layer in all of the business complexity. So again, this is an example of where being able to solve the problem faster has immense business value, but being able to solve it for representing the full complexity of your problem, that was equally valuable to this customer. And so they immediately went into production because they're seeing a return on using the technology. So.
That's great. And one of the things that we've been talking about with some folks around risk resiliency, right? The ability to build a plan and circumstances change, and now you have to replan very quickly and re-optimize based on that. So that's one of the areas where quantum enables that. And so we are doing some very interesting work with airlines and folks like that are subject to, inclement weather, right? Can you tell us a bit more about scenarios where that work would apply towards, for example, this community of modeling, simulation, training?
Yeah, I mean, at the core, I think having an optimization engine that can run very quickly, find optimal configurations, decide on a set of decision variables to optimize a particular outcome is incredibly valuable if you're basically doing a lot of, say, mission planning, or if you've got a bunch of scenarios that you want to simulate ahead of time. You might have a portfolio of 100 or 1,000 scenarios based on sort of different inputs, and you want to optimize over the delivery of, say, forces or delivery of resources to meet the demand that's caused by those scenarios. And so you can imagine having an optimization engine on the back end that is able to figure out actually how to do that delivery quickly, not just for one particular set of fixed scenarios, but in a very dynamic, changing environment. That's incredibly useful. So, and in fact, going back to this factory line example, this is exactly where they got quite excited, because they can actually run this optimization in less than 5 minutes, they can actually plan out different scenarios. So they can game out what would happen if, we saw this particular supply chain disruption, what would happen if the demand disappeared for this class of vehicle, and then they can actually rerun almost in real time on the fly. And so this definitely, being able to simulate ahead of time scenarios and make sure that you have an optimized way to deliver those scenarios is core to, I think, a lot of the problems that I think this community is trying to solve.
So it reminds me of the talk that we had just before. Wes from Andrew was talking about simulation and the impact of analyzing those circumstances of if I place my assets here versus there. So asset placement is another interesting class of problem, right?
Yep, it definitely is.
So any interesting examples to talk about there?
Yeah, I mean, so I can't talk about the actual customer, but being able to, you've got some finite amount of assets that you need to place. And this was specifically an example of tour planning. So you need to plan a particular tour. You have assets that you need to place and stops that you want to make, subject to some constraints. So you want to hit a certain number of locations on the tour. You have constraints in terms of the travel time between those locations. And so you want to place your assets such that when the tour is occurring, all those assets are available and you're minimizing some objective function. That objective function may be just overall trip time, overall cost, minimizing the number of assets that need to get deployed to hit a particular objective. So at the core, that's a hard optimization problem. And I mean, I'm saying hard optimization, I mean, the mathematical term is combinatorial optimization. And really at the core, these optimization problems, when you add a variable, like if you add a location or a city or a place to this tour, If you just add one variable, it's not that the problem becomes just a little bit harder. The solution space blows up exponentially. And so as these problems start scaling out in terms of the number of locations and the number of assets, it's not just a smooth linear function in terms of how long it takes to solve the problem. It really does blow up exponentially. And so this is really where, you, like classical techniques, really need to simplify the problem, remove some of the constraints, or remove some of the variables to solve those problems. And this is a capability, again, with our technology that we're quite excited about, being able to solve those problems at scale with the full set of complexities. So.
And you talk about Shor's algorithm, and a lot of the buzz about that, of course, is crypto and the impact to security, but also cryptocurrency, right? And I think we recently started experimenting with some quantum-based proof of work. Do you want to talk a little bit about that?
Yeah, so this is not an optimization use case, but this is a new application area that we've been exploring for almost a year now. So, and again, it's based on what Gastel talked about earlier, quantum supremacy. And so we actually published a study in March of this year showing that a particular material simulation, simulating the behavior of a magnetic material that's going through a phase transition, is computationally very, very hard for classical systems to simulate. And so we were able to model the dynamics of that material with our annealing systems in a matter of minutes. And we worked with some researchers at Oak Ridge, and we used hundreds of thousands of hours of time on the Frontier supercomputer at Oak Ridge to basically estimate how long it would take to solve this problem at scale, at the same scale that our annealing system could solve it. And we estimated that what we could solve in minutes would take up to 1 million years on the Frontier supercomputer. So this is an example of a calculation that just is not feasible at all to do classically, full stop.
A little sidebar, if I may, because the energy that would have been required for Frontier to run that problem would have been equivalent to the entirety of all the power produced on Earth for a full year, versus the quantum machine used, what, $1.50 worth of electricity?
So, yeah. So this got us excited for a bunch of reasons. One is it's showing fundamentally that harnessing quantum mechanics is giving you this advantage. You're doing something that just cannot be done classically. But then we got quite excited because we had this idea that if you harnessed a similar type of calculation, drawing these samples of a system that's going through this phase transition, you could actually turn this into a quantum hashing algorithm. And so what you could do was produce a blockchain where the core of the blockchain, the core proof of work, relied on drawing these quantum samples. And we showed with the supremacy paper that this is something that classical systems just cannot keep up with. And so now you have a proof of work that you need access to a quantum computing system to basically both do the mining and the validation. And so this got us, again, excited for a few reasons. Again, this is from the ground up a quantum safe protocol. So because you need a quantum system and you need quantum evolution to actually run the quantum hashing algorithm. So this proof of work can't get short circuited by any known means. So including classical or other quantum systems. Other quantum systems will just participate in the overall hashing. But we're estimating that the total cost of running a blockchain like this, the electrical footprint could be up to a few orders of magnitude smaller than running a classical proof of work like Bitcoin. And I think I've lost track of sort of the amount of electricity that's going into supporting crypto around the world, but I think it's approaching sort of the consumption of some of the smallest countries on Earth. Right. I mean, this is a non-trivial amount of electrical power that's going into supporting blockchain technology. So if you can come up with a way to do this in a much more energy efficient way, there's a lot of excitement there. So.
And what about, of course, we see a lot of discussion around AI, and then AI in quantum, AI or quantum.
Yeah.
Want to talk a little bit about that?
Yeah, exactly. I mean, we get this question a lot, and I think I don't see AI and quantum as being in competition. I see these as complementary technologies. I mean, AI is a set of tools and models for solving a particular set of problems. It's a set of techniques for learning data, for speaking English to people via like ChatGPT, learning the structure of data sets, being able to generate new copies of data sets. Where quantum comes in is in just the raw horsepower and being able to run these AI models. And so both on the training and the inference side. So I think the world understandably is excited about AI technologies, but if you look at sort of the data center build out, the capital that is going into building out the infrastructure required to keep kind of the models, to keep improving, again, the electrical footprint that these data centers are consuming, it's non-trivial. And so where we really see quantum actually intersecting with AI, and I can talk through some examples that we're quite excited about, is again, producing an acceleration, being able to do calculations faster at the core of the AI model, and really blunting that cost curve, that growth of capital, the growth of electrical power that's required to keep the AI kind of models, to keep that improvement happening. So, and there's a couple of examples of small-scale R&D projects that our customers have completed that basically show the path toward how you could actually see some of these savings. So we have a customer, it's a high-energy physics lab, actually, Triumph. And so they're seeing their own computing challenge in high-energy physics, where they're seeing that they're using what's called a Monte Carlo method to do their data analysis. And so these set of researchers are working with the next generation of experiments being developed at CERN in Switzerland. And they're projecting that they're going to need something like 3 to 5 million CPUs just to run these Monte Carlo chain analyses to keep up with the data that's projected to come out of the CERN experiments by the end of the decade. So this just obviously isn't feasible. They just can't build a data center there that's big enough to keep up with the data flow, so on the data analysis chain. And so they're looking at quantum generative AI models, where they're basically saying, we have a data set from the previous generation, so we want to learn the structure in the data set. We want to produce a lighter weight generative model, lighter weight than Monte Carlo methods, and predict data and generate data sets, synthetic data sets that would be expected given the particular model that you're trying to assess. So they worked with us, and they actually inserted our QPU, our annealing systems, into the model as, in the technical word, as a prior. So the prior actually gets trained along with the model. So the QPU is actually generating samples from a distribution that gets trained as part of the training process. And then when you're actually inferring on that model, you're producing kind of new copies of your data set, the QPU is providing those unique samples. And they're projecting to see up to a 10x sort of speed up over GPU approaches to doing that inference. So there, again, this is an R&D sort of result, but it's showing sort of a way forward where you can actually incorporate quantum computers directly into very large scale, like cutting edge frontier models, and seeing an advantage. So.
Cool. So how does someone get started? I mean, programming a quantum computer, does that require a quantum physics background?
Nope.
How does that work?
That's a great question. We've done a lot of work to try to make it relatively easy to get up and running with our technology. And you know, the quantum computing field and the quantum computing industry is only going to succeed if we can make it very easy to do development, to do applications, to run algorithms on our systems. And so we make all of our technology available through our cloud platform. So you basically just need an internet connection and a Leap account. Leap is the name of our cloud platform. We also have an open source toolkit called Ocean that's written in Python. You download this SDK. It's got code examples. You can come up, you can very quickly come up with your hello world example of running a quantum algorithm on our system. It's fundamentally, it's not required to have, any knowledge of quantum physics or any knowledge of kind of detailed quantum algorithms. You just need to be able to have some familiarity with Python coding and that tool set. And we do a lot of training. We have training, and we have some free class on kind of fundamentals available. So I mean, we're very keen to kind of keep the barrier as low as possible to entry. So, and this honestly is a lot of the rest of the field is also moving in this direction, realizing that training a quantum workforce, a workforce that knows how to use these technologies, is critical for driving the adoption of the technology.
100%. So. How about we open this up for some Q&A? And folks, this is a dialogue, so please feel free to step up to the mic. I'm going to check on Slido here and see if we have any questions.
I'll bring the mic. All right. Hey, thank you for this. It's cool technology. I'm curious, how do you envision quantum for defense applications in the future? Where does the value of this really come in? And if you're able to even maybe neck it down some into the modeling, simulation, and training community applications.
Yeah, I mean, at the core, what we can offer is an engine that optimizes, that basically finds optimal configurations for very large scale, very complicated problems. Coming up with a set of decision variables that optimizes a particular use case or a particular objective function is the core of our platform, of what the technology can provide today. So I think in the context of simulation and modeling, I mean, I can imagine, we saw examples of some, the need to basically, place assets, optimize the placement of those assets in simulation runs and training runs. How do you actually decide how to route those assets through like a contested environment where there's quite a bit of constraints on sort of where you can actually move these assets through. So all of that at the core is a hard optimization problem. So like once you've got sort of your landscape, you're wanting to run the simulation, and every step of the way there's hard optimization that needs to get solved in order for you to actually really understand and run that modeling and that training. So I really see this as it providing a computing engine that will allow you to like expand the scale of your simulations and the modeling environment, and maybe even the speed of those simulations. So and while not blowing up the cost of doing those. So.
To what extent have the promises of the early theorists of these massively parallel, instantaneous computations that could never be done conventionally, what extent has that been abandoned? I mean, what you got here, and I'm no quantum guy, but what you got here, it seems to exploit some quantum phenomena. But in some ways, it's really high-speed computing. In some ways, it's sort of analog computing. I mean, you kind of got an interesting mix of those. Is that original vision gone, or is it still?
Nope.
Still
No.
there?
No,
And
it's.
is error correction the main thing that's holding us back?
So with annealing systems, you're absolutely right. It's not error corrected, so it's not digital quantum computing. It's very much an analog quantum computing technology. And in fact, all pre-error corrected technologies are analog based. But with annealing systems, the promise really is that there is a massive advantage in searching over these very complicated landscapes to find optimal configurations. So, and there's actually, I can follow up with you on like the detailed theory that shows like why you would expect quantum dynamics to give you this massive scaling advantage in that search. And not only is there solid theoretical evidence from the last 20 years, but the empirical evidence is building up as well about that gap that you're opening up because you're harnessing quantum dynamics for this search capability. So in the case of gate model systems and, eventually, Shor's algorithm, I think, a lot of people are watching carefully the maturation of those technologies. I personally don't think that cracking RSA is a good commercial use case for quantum computing. I mean, I understand why there's a lot of interest, but I think that the real killer app and the real kind of explosion in economic benefit is going to be coming from the quantum chemistry and the quantum materials side.
So let me just segue because there's a question from Slido that sort of fits there, which is, when do you think quantum computing becomes mainstream?
That's a great question. I mean, one way to answer that question is, when does quantum computing become commercial? And it is commercial today for optimization. For the annealing systems that we built out, the technology is delivering commercial value today. Gate model systems and really solving what you're calling that error correction challenge, we think is probably 5 to 7 years away. But I think and this goes back to the kind of the question around programming and ease of programming. One of the main things that is going to drive quantum computing going mainstream is just this communications gap. Really, I think that one of the myths that like I think I'm trying to puncture with fireside chats like this is the idea that this is a technology that's 20 years away, 30 years away. You don't need to worry about it. It's not. It's developing quickly. It's commercializing very fast. I think it's poised to go mainstream over the next decade.
Great.
Thank you so much, first of all, for explaining all the concepts very clearly and definitely increased my knowledge gap, so agreed with you increasing the IQ points. So my background is in aerospace simulation, and at work we build like flight simulators, and with flight simulation, the constraint space is very dynamic and changing. With things like weather, you have traffic patterns, you have, like, it's very mission specific.
Yep.
So with quantum annealing, like, what would you say the main limiter would be in those situations? Would it be like the embedding, the noise, the latency of the solver? Or would it be like, how does it respond to real-time changes? Does it need to stop and rerun? Or does it constantly optimize the search space?
So one of the things is latency. So I mean, we have a real-time cloud platform where APIs respond in real time, but they're in the cloud, and so there is going to be a handful of tens of milliseconds for response time. And so really for the customers that have these hard optimization problems, that is not an issue. But if you need sort of sub 10 millisecond response times, that would be a hard requirement with the current architecture. So I mean, the ability to respond quickly to changes, I mean, that again comes down to latency. So we can respond, but the latency is going to be in the tens of milliseconds.
So technically speaking, if one were able to encapsulate the system and the cloud layer minus the cloud, but a direct connection, that would eliminate that latency.
Would reduce it for sure. So yeah. Yeah, but I mean, again, it depends in the details of what the requirements are for that latency. So, I mean, you asked a little bit about kind of variable count and noise, and I think, I'd say the optimization areas where we're really seeing advantage. We have a sort of a hybrid solver stack that will basically pull in problems that have up to 1 million variables on the front end and then make the calls on the back end to our quantum system. And so we haven't been limited at all in terms of the scale of the problems and the amount of constraints that we can actually layer onto the problems to date. So.
That's good. Thank you. Excited to see what's next.
Thank you.
Hi, I want to thank you for the great conversation so far. It's been very intriguing to listen to all this, and something that was remarkable was really the energy efficiency with quantum computing, and really the current landscape to where we have such a energy crisis and shortage with the current AI infrastructure build out. What's preventing quantum? What's the breakthrough that is needed for this to become more commercialized and something to where are we making the right expenditures right now as investors and everything into our current infrastructure versus appropriating those over to quantum?
Yeah, that's a good question. Yeah, so I'd say the build out of the data centers and the energy footprint is staggering. I think our current systems draw about 12 kilowatts of power, and that's been fixed. That's one of our annealing systems that's been fixed across sort of 6 product generations, and so we're seeing the capability of the technology grow exponentially without any real change in the power draw. So I agree, that's exciting, and I think that's a real kind of value for the quantum industry as a whole going forward. So, I mean, I think we're early days in terms of sort of the proof points of quantum computing accelerating AI, and so I mean, I think there's a good reason why there's a build out with these big GPU clusters right now. But I think we're making some heavy investments, and so are our customers, in showing those proof points to show that, yeah, you can actually do things more efficiently with quantum computers. And so I think I would keep a very close eye in the next year or two on sort of the quantum algorithms and AI models that incorporate quantum algorithms, because I think we're going to actually start seeing some of those reductions within the next couple of years, not just in the lab, but sort of for more commercial use cases. So
thank you, and that goes also to what you said. AI and quantum aren't necessarily in competition.
No.
Working in tandem, so
Yep.
you can still justify the large expenditures there.
Yep.
Hi there. So my question is, in the same way that AI sometimes runs into problems with hallucinations, and if you're doing hashing, you can have problems with collisions. Are there any problems, bottlenecks, or things that you're coming across in quantum computing specifically, errors that you're working on overcoming? Are there any big potholes like that you guys are working around at the current moment? Just something that those of us who are not super familiar with quantum might not be aware of, but something to keep in mind as we're looking into it further.
Yeah. I think annealing systems are heuristics. So there is, when you're running an annealing algorithm, you're not guaranteed, and you don't get the same answer every time. And so There are times when you, for example, run the annealing process and you get a near to optimum answer, but not an optimum answer. And so, that's for some users that not having that kind of guarantee of optimality can be an issue for some use cases. So what we're finding most of the time is that, and if you look at kind of the operations research community, what really matters is solution quality is a function of budget in terms of time or money. And so you don't necessarily need to get to optimal, you just need to get below a threshold faster than some other competitive technology. So, but I mean, that's just full disclosure, like it is a heuristic, and so there are cases where you're not getting the optimal answer. So, I think we would like, and we have plans with our next generation processor to scale up the device count. So, and I think that's primarily to open up the set of use cases over which we can actually show, a commercial viability. So, but I think, the field, the quantum field in general, the quantum industry in general, has to scale up these technologies. So, and again, this is why we're so convinced that superconducting approaches are the best way to go over some of these other approaches. We don't need to solve the same problems that the CMOS and semiconductor industry have solved. We're basically using all that technology. But scaling, especially on the gate model side, is going to be critical. So,
Thank you.
no problem.
Tough being the short person, right? So simulation has struggled with the ability to scale the number of entities that fill up the space, right? And especially when you're counting entities as more than just individual vehicles or individual soldiers, but now you're starting to consider electronic devices and sensors and things like that as also part of the landscape. One approach to modeling that has been agent-based modeling. I don't know if you're familiar with that, but that's one of those things that is kind of emergent in its behaviors, right? You set up those rules and the agents will go do their thing, and a larger behavior then emerges from that environment.
Right.
So is the annealing method aligned with the way that agent-based modeling represents behaviors so that it can be applied there, or do we need to rethink how we do agent-based?
I think it depends on where, if you move to the agent-based architectures, where is the computational crunch then? Is it coordination between agents? Is it basically just the compute required to run all of those agents sort of semi-independently? I guess I don't know enough about where that computing crunch is to comment directly, other than just say that, like, the scaling of optimization is basically a critical problem for a lot of our customers, and they're hitting a wall and they're hitting a computing crunch with their current classical traditional approaches. And that's where we can come in and offer an advantage, where we can actually solve problems at much bigger scale than they're able to solve today with their technologies. So again, this is the first time I've been to like the simulation modeling conference like this. So I think we'd want to understand where the real computational crunch is happening with the agent-based framework or paradigm. But at the core, I think what we offer is a much more scalable way to do hard optimization problems.
So I would add two things, right? One, we recently had a chance to sit down with a prominent software company that I can't talk about who it is, that is very deep into agentic models and implementations. And one of the things that they brought to us as a use case is, how do we optimize the right quantity of agents for given tasks in a very large environment, right? That was one of the problems they brought to us. But the second one, I think, on simulation specifically, is a conversation we had on the floor earlier today around movement of individual units or higher echelons. How do you calculate and route that through a terrain mesh? So, right, that would be an interesting example of a problem that grows exponentially in complexity. The bigger the number of the units and routes that are available, where a annealing quantum computer could help.
Okay, thank you.
Hi, good afternoon. Diego Torrese from Italy. So I have a couple of questions for you. The first one is, what are the methodologies for embedding quantum annealing algorithms into generative model training workflows to enhance global optimization across high-dimensional parameter spaces? First question. And I go with the second one. what error mitigation and qubit calibration techniques are required to ensure the stability of quantum solutions in operational environments with, for example, high electromagnetic noise?
Okay.
Thank you.
Okay, great. I'll answer the first question around the generative AI, sort of where the annealing systems fit in. So the example that I'm going to cite is, again, this high energy physics generative AI model where there's a data set. There is something called a variational autoencoder that will map that data set into a latent space that's discrete. And then our annealing systems basically are trained on that discrete latent space to provide samples with a particular weighting that matches the input data. And then there's a decoding process, again, so there's a neural net on the input and a neural net on the output that basically map your data from your initial data set to this discrete space and then back to your data space. So, and then what we're doing with the QPU is training it in this latent space and training it to basically match a particular configuration that we're seeing from that data set so that then you can actually sample novel samples from the QPU and then do the decoding and have novel samples from your data set. So that at the core is how we're, so I mean the term for this that we use is the QPU is a prior to the model that gets trained. And so then you can use it then to generate new samples that fit a particular data structure. So, and in general, that sampling is a hard problem. And so that's we're really investigating what the potential advantages are on that sampling side. The second half of your question is how do we operate our systems in these operational environments that are subject to drift or physical changes? We have had systems in the field at customer sites since 2011. So I think our very first commercial sale of the D-Wave 1 technology was to Lockheed Martin, and that was an installation in Southern California. So we actually have quite a bit of automatic telemetry. So we're actually doing regular diagnostics, running these very small-scale algorithms that are designed to elicit any sort of deviation in behavior, and then correct it automatically. And so these are running on a fairly regular cycle. It's probably a small percentage, maybe 1% of the duty cycle of a quantum system. Our systems are involved with this kind of self-diagnostics and correction. And so we've had systems in the field, like Gustavo said, continuously for years without needing manual intervention. But it's critical. Like you do need those automatic routines for assessing the health and the performance and making sure that the performance is within some bound.
And by the way, we just announced a system going into Italy. So that there's a quantum alliance, and so in celebration of the 100-year anniversary of Alessandro Volta. And so you will see, if you probably can look it up online, but you'll see the announcement about one of our systems deployed in Italy.
Thank you so much.
How you doing? Ray Compton, fellow. Great talk, especially when you look at discussions of synthetic data for AI. So I want to take it a different approach.
Okay.
Strategic. So, if we look at, this is new technology, and in a sense, in the baby world of that. And it's a sense, when we look at what's going on with the government, with acquisition reform, OTAs, CSOs, and stuff like that, how do you look as a company to advise the government, or how do you see this type of technology being contracted? One thing we know about quantum, hardware side of the house, if you want to call it the software, so you look at it like quantum possibly coming in as a cloud base with some type of SSA, service as a software as a service type of thing.
Yeah.
How do you project it, and even ask the question, how would you like to see the government contract it, as a product into technology, into systems?
That's a great question. I mean, our primary model that we're using for our commercial customers is something we're calling quantum computing as a service. And so you subscribe to our Leap Cloud platform. This gives you access to cloud-based APIs. This is a mix of hardware and software. So there's an API layer, but you're making on the back end calls to our quantum system. And so this has been a very, very effective model at bringing this technology to a very broad set of users. And so my first remark would be, the cloud-based access is working extremely well commercially. We would very much like to have that continue to work for government users. So again, I think we have an internal professional services team at D-Wave that will work closely with commercial customers to really do discovery on the use cases that best match to our solvers. And we're actually, very open with some customers that bring us a problem, and you just don't need a quantum system to accelerate it. It's at the core. It's not a hard optimization problem. But we have now a growing set of problems that actually are actually hard optimization problems where we moved into production. And so really kind of understanding, working with our professional services team on the discovery process to figure out sort of where the best fits between sort of the use cases on the government side and our technology are. So, and then, on the government funding side, I'm encouraged, the government to look at funding near-term applications and near-term application development. I think a lot of the funding that's come from the government in the quantum space has been really heavily skewed toward kind of R&D and hardware development platforms, and really the bridge between that and use cases, the funding is light. So I'd like to see a lot more funding for kind of application development and emerging applications.
And to add to the answer to your question, we've recently announced, and the gentleman's sitting right back there, Jack, say hello. Jack Sears joined us to help us in land our U.S. government dedicated services and sales organization. But one of the things that we like to do a lot is to partner with people. And so we're open to conversations with anyone that wants to build applications on top of the platform. And also, if anyone's interested in learning more about that, we have our big user conference coming up in January in Boca Raton, Florida. And one of the things we'll have there is a dedicated public sector panel where we're going to touch on a lot of these, both policy and acquisition type scenarios. So folks, with that, I think that was all the time we had for today. Thank you so much for your participation and your questions. Thank you, Trevor. And a round of applause, please.